If we think about particles being the sum of many overlapping waves, however, this suddenly makes a lot more sense. Take a look at this wave. It is perfectly defined in terms of where it is going,
Those Mandarin,
but
yes.
if we consider the peaks of this wave to represent the location of the subatomic particle, or at least the possibility that the particle is at this location, there are a lot of places it can be. So, for this given string, we have perfect knowledge as to its speed and direction, but are uncertain about its position in a given space of string, perfectly in line with Heisenberg's uncertainty principle. If we converge several different waves into a single point, we can take advantage of Fourier's mathematical trick to cancel out some of the peaks of our wave. The more waves we add coming in from different directions, the more our particle becomes defined in space. But look at our particle now. How many strings are running through it? Each of these is a separate vector line, representing momentum in a different direction.
Analyzing sine waves. Is that what I'm thinking? Sine, angle, sine, 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 sine. Wait, no, that's not. Wait, I forgot. I remember I used to calculate that stuff, but I totally don't know what that meant. And I got a 3 out of 100 in math class.
It's no longer quite so possible to pin down where this particle is going next, as there are several options that could be true. Perfectly pinning down a particle in terms of its location would require vector lines that could lead anywhere. This is starting to get into territory where you would need information from the entire universe before a single particle can be truly solved in terms of its location in space and time, which is a little headache-inducing. Perhaps the universe makes do with close approximations most of the time, until someone looks closely. For this model, we must discard our concept of a particle as a localized object,
blue, 1 brown.
but instead we define them as the convergence of different waves, coming together at a single point and then diverging again. This divergence doesn't feel right to us. We are uncomfortable with the idea of our particles only being really there at a given moment and dissipating afterwards. However, those of you familiar with the double slit experiment, which I have covered in an earlier video, will recognize that this is an uncanny match to another odd experimental result.
The slit experiment.
A single photon released from an emitter and passing through 2 slits will somehow pass through both slits, interfering with its reaches the far detector as a single particle again, indicating a new convergence at that point, but by sending many photons along this path, it becomes clear that interference is taking place in the intervening space. The photon seems to leave as a particle and arrive as a particle, but in the intervening space, it takes on the properties of a propagating, rippling wave. Already we begin to see how some of the strangest aspects of the quantum world fit with the idea of strings carrying waves of energy. But this is only the first part of my model. To really see how much a theory matches the universe around us, we need to explore the motion of particles across time and space, to better understand entanglement and superpositions. And to do that, we need to explore how strings lead to gravity, time dilation, and other principles of relativity on larger scales. We need to have a clear concept of how time works. My model accommodates that, but it will have to wait until my 3rd video.
closer. Okay. I'm gonna get some fruit right now. This is like what Miso experiences on the daily. Me sniffing. Wait, so like... Ah. Don't know where it's going. Because it's unpredictable. Okay. So, I'm gonna grab some fruit, guys. BRB. Hey guys. Mimi, sorry. Okay, I don't know what Mimi wants. Oi! Come on! Come on! Come on! Wah! Okay, he wants raspberries, but I cannot give it to him. He has weak tummy. He wants cuddle? Nah, he just wants food. Miso does that sometimes. But usually, if I don't have food, he's going. Look, he wants to go already. Oh! Jesus. The next topic. Yeah, wave function, superposition, quantum entanglement. Wait, string theory. I think string theory was kind of related to that. You wanna sniff his paws? I know, his paws so good. Oh my god, oh my god! Wait, you guys. Guys. Oh! Did you guys see that? Was it in frame? Oh! He smells so good, you know? Like, every day, Kumi and I are just shocked at how good he smells. Also, I have been really liking this bread, like, on its own. It just tastes good on its own with nasi. And then I feel like a child again because I used to eat just bread by itself. It's like milk bread. What does it smell like? What does miso smell like? He smells a little salty. I'm 되게. Oh my god, he just smells so good. Like, can I show you guys? He smells so good. He really wants bread. Babe, you cannot eat this. No raspberries for you. No! 去瞓覺. Guys. String theory. Replaces point-like particles with one-dimensional strings as the fundamental building block to the universe. Ah. So it's related to wave frequency. Mm. Mm. Hi, GPO. Okay. Ties into this. It's all
For instance,
related.
in the following situation. We start with 2 electrons
Bye-bye.
motionless.
Good night, Lord.
Over time, the 2 electrons progress towards the future. At first, one might think that the 2 electrons remain motionless indefinitely. But that would be forgetting that our electrons are constantly moving through the photon field, with which we allowed them to interact.
Hi, Tofu. I love Tofu.
We saw that a quantum field realizes all possible evolutions at the same time. In a way, each evolution describes a scenario, and in some of these scenarios, the electrons will interact with the photon field. In this scenario, for example, the electron emits a virtual photon at a certain instant, which carries away part of its momentum, and the virtual photon is absorbed a little later by the other electron.
Strange.
In this other scenario, the electrons exchange this time 2 photons. Or again in this third, more complex scenario, the electron emits a virtual photon, which is converted into a pair of virtual electron and positron that annihilate together into a virtual photon, which finally ends up absorbed by the second electron. By exchanging part of their momentum, carried by virtual particles, the 2 electrons will in some scenarios get closer, and in others get further apart. Now consider the following analogy. On a guitar, a string can vibrate with different frequencies, each of which corresponds to a pure sound. But when we pluck the string, it starts to vibrate in a superposition of all these frequencies with more or less amplitude. And the synthesis of all these pure sounds together with different amplitudes is what makes the total sound produced by the string. Similarly, a quantum field evolves according to every possible scenario with more or less amplitude, and it is the synthesis of all these scenarios together that describe the real evolution of the physical system. In particular, in our example, when we add up all these possibilities, we observe that overall our 2 electrons are more and more deflected. They feel a force repelling them because of the
Oh my gosh. Oh.
Does anyone know of people like
Oh my
Michio
God.
Kaku that can explain string theory like he does for people like me? And I'm not a genius. Well, I am Michio Kaku, and I'd be glad to answer that
Hello?
question. First of all, most textbooks say that an electron is a dot. Particles that we see in our atom smashers are dots. But if I had a super microscope, I can see that that dot is actually a rubber band. From a distance, this rubber band looks like a dot. Close up, you see that it's a vibrating string. Now, this rubber band can vibrate in many different modes. Each mode can be called a particle. So, for example, this might be an electron. But if you twirl it in a different way, it becomes a quark. And
It's
if
a
you twirl it
raspberry.
this way, you have to give it a
Could be
different
brain.
name. We call it
yum.
a neutrino.
Oh. Okay. Next up, we have this. Hey, welcome in Cena M01. Quantum entanglement, guys. It's like me and this mic. Two or more particles become linked in such a way they share the same fate, regardless of the distance separating them. Measuring a property of one entangled particle instantaneously influences the corresponding property of the other. A connection that even Albert Einstein famously called spooky action at a distance. This connection is not a form of fast and light communication. Is the outcome of the measurement is random until it occurs. Oh! You know, sometimes they make people like touch, and then they can feel touch like two people, and then you only touch one person, but the other person can feel it too. I think it's like entanglement. Is that right? What do you mean always connected? What do you mean? How do I show you guys in a better way? Right here. Yeah. Okay. So dark matter and dark energy. Yes. But how do you get entangled in the first place? Same origin. They shed their original quantum state, take on a new united quantum state. Conflict with relativity. Hey Nikki. But like, what do you mean same origin?
Quantum entanglement is one of the most intriguing and perplexing phenomena in quantum physics. It allows physicists to create connections between particles that seem to violate our understanding of space and time. But what is entanglement really? These two coins are not entangled. If we flip this coin, it won't have any effect on the other. Each coin, when flipped, will have a 50% chance of landing heads or tails. And that's true. But what if could do some magic trick to entangle these coins so to one comes up heads, the other will come up tails, no matter how far apart they are. Let's say I give this coin to Alice and this one to Bob, just before they set off on rocket ships going in opposite directions. Alice and Bob are each under strict instructions not to flip their coins until they've
Hey,
been
Blue.
traveling for 10 years. When the time is up, they each flip their coin and immediately send radio signals to each other with the answers. But while those signals might take years to reach their destinations, the entanglement means that the moment Alice sees heads, she knows that Bob's coin landed tails, and vice versa. Alice doesn't have to wait for Bob's radio signal to arrive to know what it will say. Alice's coin had a 50-50 chance of coming up head of the time. Because Bob's signal is still traveling to her when she finds out the answer, it's as if Alice has predicted the future. This might sound impossible, but it's exactly what quantum entanglement does to individual particles. An way to set this up is to ensure that they will have opposite spins, meaning they'll line up opposite to each other in a magnetic field.
God damn it!
Then you separate the particles by thousands of miles and measure the spin of one of them. If you find that its spin points up, the others will always point down. Like in the coin example, whenever Alice measures the spin of her particle, if it has spin up, she'll instantly know that Bob's particle has spin down, or vice versa, no matter how far away they are. Einstein called this spooky action at a distance. Because according to his theory of relativity, no information can travel faster than the speed of light. You shouldn't be able to know anything about the other particle before a light beam with the information can reach you. Entanglement seems to throw this idea out the spaceship airlock.
God
To
damn
be
it!
clear, however often it's described that way in science fiction, this is not faster than light communication. Just like with the coin flip, the state of the entangled particle in your possession is random. You can't know ahead of time if it's spin up or spin down. All you know is that when you measure it, the other particle will be
What?
the opposite. Even if Alice
What,
and Bob
Nami?
tried to agree ahead of time on some kind of code to use for a message, they wouldn't get to decide what message they were going to send. It would just be random gibberish. Well, we can't use quantum
What?
entanglement to communicate instantaneously. We can use it in technologies such as quantum cryptography and quantum computing, which we'll discuss later.
Big.
Wordy and kind of conceptual and not very practical. And it took another 20-25 years
big.
before an Irish physicist,
My
John Bell,
big
kind of
driver. Oh,
turned his
white
ideas
rage.
into an equation. If entanglement didn't exist, the equation would be satisfied. If entanglement exists, it would be violated. The world is quantum mechanical. This is absolutely amazing. This is something we cannot understand with our usual concepts of classical mechanics, but it is there, it exists.
Quantum entanglement is certainly strange, and we still don't completely understand it. But it is a feature of nature, and it's an incredible tool.
No, what do you mean from the same origin, though? They can be entangled by being produced together in a single quantum event. So, like twins? No. Simultaneous creation, yes. Do you have more